So before we dive into the isomorphisms in trees, yeah, I want to say thank you for these incredibly detailed reviews of my last video, or can I say here, I want to say a genuine thank you for
Okay,
genuine,
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 genuine.
genuine, yeah.
Oh no, you're always genuine. Okay, no, you spend a lot of time, Vadim. You spent a lot of time learning English, and I just want the best results for you. So, yeah, so kind of the same way with your math, right? Yeah, so with your mathematics, right? You work very hard with mathematics, and of course, you want results. So
Yeah,
yeah,
so yeah,
in time, these corrections you won't even remember them anymore. You will do it naturally, and so
yeah, yeah,
it'll be So yeah, it'll come very naturally.
yeah. Well, so yeah,
So
thank you. In your corrections,
yeah.
you pointed out several such recurring things, recurring mistakes. Yeah,
Well, but
missing articles. Yeah, prepositions, word
well,
usage.
yeah,
Yeah, so
but Dean, I make okay in Russian. I make the same mistakes over and over again. I'm surprised your father is not angry at me. I'm surprised he is not angry. But it's just hard to concentrate for a long period of time and remember. But gradually, he said, your father says I am improving, and you have improved also. Yeah, so it's a
yeah,
very but
yeah, yeah,
be patient with yourself.
yeah. So
Yeah,
well,
so
I
it
think
just uh, it's a lot to remember. There's a lot of things to remember, but after a
yeah.
period of time, it comes naturally. So
Yeah, well, yeah, so I think these details actually matter yeah, a lot in technical explanations, yeah, in computer science
okay,
English. Yeah, so
sure,
for
yeah,
example, with
yeah,
these articles using such as we'll look at the relationship of tree centers, at the relationship of tree centers. Yeah,
yes,
this, for
right,
example, here, one tiny word, the, but it changes, it sounds like it came from a technical talk, or so can I say here, like this phrase belongs in a technical talk. So can I say like this?
right, yes, exactly. It sounds like if you say we'll look at the relationship of tree centers, it sounds like you're a teacher or a computer science instructor, right? Or if you say there can be more than one center of a tree, or there can be more than one center, you sound like a teacher. The tree's longest path. Yes, that's something a teacher would say, right? So don't feel
Yeah.
bad. I mean, you're 14 years old. So you you have a long life ahead of you. So yeah, be patient with yourself.
Yeah. All right. Yeah. So these
Yeah,
corrections is what making the natural academic English. Yeah.
yeah.
Uh,
There you go.
yeah. So these uh, these also prepositions at. So well,
Yes, yes.
last time I really yeah like dropping
Well,
at in these discussions.
well,
Yeah.
but you don't know. I mean, it's not your native language, right? Okay, so
Yeah.
it's okay. Like uh, be patient with yourself. I'm patient with it. I feel like, well, it's not his native language, so how does he know? So that's all. Yeah, and I hope your father feels the same way because it's like, oh my gosh,
Yeah.
same same mistake. But gradually I am improving. So and you are too.
Yeah. Yeah, yeah. So, Well, I think that these small details in language matter, especially in computer science. So maybe this precision in language supports precision in thinking and in explanations.
Yes,
Yeah.
it
So
will help.
well.
It will help in time. In time, it will help. Yes, you will see.
Yeah, all right. Yeah. Thank you. So today I
Sure,
wanted to
no
talk
problem.
about these isomorphic trees, hopefully with better articles and with fewer missing prepositions. Yeah. So I want to
Okay,
start.
okay.
1 moment. I wanted to start by talking about general graphs and ask when two graphs are isomorphic. So we are asking whether they are structurally the same here. So here on the slide in the middle, the question of asking whether two graphs are isomorphic, that is just mean whether they're structurally the same. So these two graphs, J1 and J2, are labeled differently and they may appear differently, and mm, their indices are different, their nodes are different. However, they're structurally the same graph. So we could, for example, unfold the graph on the right, unfold the J2 graph to
The
match the one
G2
on the
graph.
left.
The G2.
Yeah, yeah, thank you. The
G2 graph,
G2
not
graph.
J2. Yeah, no
Yeah,
problem.
thank you. Yeah, J2 graph for it
G.
to,
No, 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 no.
yeah, G.
G2. G2.
Yeah, all right.
G. Not J.
G.
J is a different letter.
Yeah, yeah, J2. Uh,
No, no, G. G.
G.
G. Sorry.
G. All right.
G.
G.
Sorry.
All right. All right. G. All right.
Okay.
Yeah. So uh, these varieties of second graph on the right, we can relabel them and would have two identical graphs. So it is for them to be isomorphic, their structure just have to be the same, not these varieties names, whatever. So how can we define this more uh, more accurately? So how we can define the notion of a graph isomorphism? So simply saying that two graphs have the same structure is not well defined. So we can define a graph G1 and G2 and their set of edges and vertices E1 and E2 and V2 and E2, and we can say that two graphs G1 and G2 are isomorphic if there exists a bijection, if there exists this bijection function between the sets V1 and V2, sets of their vertices, which such as that for all pairs of vertices of from each form an edge in G1, applying a function, this bijection function phi, to the nodes. Yeah, for all edges always result in an edge which is presented in the graph G2. So to put more simply, for an isomorphism to exist, there needs to be a function, a bijection that can map all the nodes in G1 to G2 and vice versa. So we just want to determine such a bijection function here. So also determining if two graphs are isomorphic is not only not obvious to the human eye, but also a difficult problem computationally for computers. And however, this problem of defining a isomorphism of a graph is an NMP complete problem. So we cannot perform an algorithm that would work for every graph that would be that would be enough efficient for our purposes. So, for example, if we would have a large a large graph with a lot of vertices and a lot of edges, its time complexity would be not enough to determine is it isomorphism is isomorphic or not. However, for graph subclasses, there are algorithms that can determine whether the graph is isomorphic, whether this type of graph is isomorphic or not. And for example, for such a class of graphs as trees, there is such a algorithm to determine whether the graph is isomorphic or not. So many polynomial time algorithm exist. For example, for trees. And let's have a look at examples of isomorphic trees. So here, these two trees are not isomorphic because they have different structure. They're structurally different, and for human eye, that may not be obvious. And for example, these two trees are isomorphic. So the possible mapping, the possible bijection is such at the as at the end of at the bottom of the screen. One moment. Yeah. So in terms of writing an algorithm of identifying isomorphic trees, whether the tree is isomorphic, there are several very quick, usually hash-based or most often hash-based algorithms to identify isomorphic trees. So they tend to be fast, they tend to be efficient. However, they also error prone due to hash collisions in a limited integer space. So the algorithms that are using hashes often break due to hash collisions because here hash functions and hash algorithms are not as accurate as we want to. And the method we're going to look today involves serializing a tree into unique encoding. So we want to encode each tree in one way. So if we have two different unrooted trees, for this algorithm to be possible, we want to represent them in one type of a representation. So if we are using one type of representation, for example, if we root a tree by its center node, and if two trees have the same encoding representation, that means they are isomorphic. Yeah, so when going about encoding a tree, we can directly serialize an unrooted tree, but in practice it is much more easier to write code to serialize a rooted tree because when we are writing this serialized representation of a tree, of an unrooted tree, it might be non-obvious at which point to start this encoding, and also this may result in a not working algorithm for some types of trees. Yeah, however, we are going to look today at encoding a rooted tree. Alright, another important thing to talk about is that, a little caveat to watch out, a little here, some kind of exception or something. So if we're going to root our trees, T1 and T2, we must check if there is a to check if there is a morphic, we need to ensure they're rooted with the same root node. We want to select we must select before encoding the trees the same root node, and the most efficient way to find the root node of a tree, the most how to say versatile way to find the root of the tree is to center it. So we want to find the centers of the original tree, and next we'll look at how to handle the case when either tree can have more than one center, because we know from the last talk that a tree can have two centers, and now we'll look at how to handle this exception or something. Yeah, so we want to root the tree at the center node, and then we want to generate the encoding for each tree and compare the serialized tree values for equality. So, for example, for these two encodings, that is the sequence of left brace and right brace brackets, right and left brackets. However, you might think of 0 and 1s and whatever. This is just for convenience of
onion. Yeah, onion. Onion.
Oh, one moment. Yeah. So this is just for the convenience. Yeah. And we compare these to numbers or to strings of brackets, whatever. So if they are the same, if they're equal, that means that these two trees are isomorphic. So, like in this case, they are isomorphic. So also from this encoding, it should be possible to reconstruct the original tree based on the encoding. So the algorithm that allows us to encode the trees, the algorithm that makes it possible to serialize them, is known as AHU algorithm. So that is a clever serialization technique we're going to use to represent a tree as a unique string. This is how we're going to look at this. And also an important note is that unlike many tree isomorphism invariants, this AHU is able to capture a complete history of a tree's degree, spectrum, and structure. This allows us, and also it ensures a deterministic method of checking for tree isomorphism. So this is maybe one of the best, one of the most efficient algorithms to define whether the tree is isomorphic or not. So let's take a closer look how this technique works. This Hillman algorithm works. So, for example, we have this tree and we want to encode it. So, at the beginning, why this slide is not changing. So the first thing we want to do is assign all leaf nodes with these empty tuples, so that is just the pair of right and left bracket, and we can determine as whatever, for example, 0, 1, 1 and 0, whatever. Yeah, and next we process all nodes, all the parent nodes of these of the nodes we have just processed, for example, using a queue. And after that, for all these great our children, we want to combine their these tuples of these strings, want to combine them with the new pair of brackets that would represent a parent node. So in this way, we would add into a new pair of bracket nodes, would add within it into this pair of its child nodes. So in this case, this way it would work. And also, yeah. So now on the slide, these pairs we added are highlighted. So that is more. It's more visible how it works. Yeah. So yeah, it's clearer when we highlight them. And if we continue this process to process into to process the child nodes, these nodes in gray, then we'll see that we have combined the labels from 4 to 5 and create nodes 1 new label, and so on. So we're continuing to do this, and maybe one of the most important things here, as we would notice, is that in the combining phase, the child nodes labels need to get sorted. So this is what ensures uniqueness of a tree representation, of a tree encoding. So we need to sort these. We need to sort these child nodes when we're adding them. And also, an important note that an opening bracket, of course, lexicographically less than a closing bracket. So, by the way, we need to sort them by the amount of child nodes within of this child node. Yeah. So we want to sort them by the degree of these nodes. And this is why this algorithm is such efficient. So this is how we get to process the last node, and this is like the encoding, the serialized encoding works. Yeah, we have just to sort the child nodes, and as we sorted the child's nodes within this root node, we now serialized encoding. We've created this thing. So this algorithm, AHU, is one of the most neat and clever algorithm to make the representation of the tree, and it may not be useful in not only in this problem, but the representation of the tree using these brackets is at all pretty wise thing. So the creators of this algorithm yeah, made such a neat thing. So in summary, what we've just looked at. So the first thing we've done is that leaf nodes are assigned this Knuth tuples of a pair of brackets. And each time we move up a layer of the labels of the previous subtrees get sorted lexicographically and wrapped in brackets that represents the node we're now processing. And also, we cannot process a node until we haven't processed all of its children. So in this case, we get up on the tree. That is the algorithm of the tree that works from the leaves to the root node. So let's look at some pseudocode briefly. So the function trees are isomorphic takes as input two undirected trees, tree 1 and tree 2. Yes, they are sorted in adjacency lists. And the first thing we do is find the center nodes. That is the method we have looked last time. So as we get the arrays of their tree nodes, we want to root that tree with the first center node. So they might be two center node, and this within the first tree we want to root it with the first center node we found. So the root method is the method we looked at 2 talks ago. Yeah, so as a reminder, this is how the tree node object class looks inside. Yeah, so well, within using this class, it facilitates writing recursive algorithms on these recursive algorithms on trees, and also they're making the tree data type, data structure organized. So well, each node has an ID, has its parent node pointer and its child nodes pointers. Yeah, so once we have rooted our tree, we can serialize it using the encode method. Let's look at how it works inside. So as we have, yeah, so this is how it works inside. So the first thing we do is handle the base case where we have a null node. So for the null node, we just return an empty string that will cause all leaves node to have a left bracket and right bracket upon the callback. Yeah, so for each node, we maintain a list of labels for all of the subtrees. So to generate these labels, we iterate through all the children of this node and recursively call the encode method, adding the results to the labels list. So that is the recursive part. Yeah, so next, after the loop, after this recursive, these recursive calls have returned, and the labels list is populated, so we want to get it sorted. Yeah, so afterwards, we want to concatenate the labels and wrap the results in brackets. So this is the encode method for a node. And because it is recursive, at the end we would get the encoding for the root node, that is the encoding of our tree, as we've looked before. So coming back to the main method, now the next thing we want to do is encode the second tree and compare encoded results. So however, the second tree might have 2 centers, and we don't know which is the correct one, so we need to try both. And here we can, of course, make 2 if checks. However, even at series, our teachers guided us to if we want to make multiple checks, even if there are 2 checks, we want to write for cycle when we iterate through each possible scenario, because this copy-paste code looks very ambiguous, and sometimes our teachers at series even rejected solutions with a load of copy-paste code because it is just unreadable. Yeah, so here how this block of code works. We are just iterating through the second tree centers. There might be 1 or 2, and for each center, we are rooting the tree with the root node of the center we are now processing. We are encoding this tree, and if these encodings are equal, we return true. Otherwise, we continue the cycle with the second center, so whether it's true or we are exiting the cycle and returning false. So this is how this function type function isomorphic check works. So well, that's it for the pseudocode, and well, I'll wrap up here. Thank you, Robert.